welcome back to the deep dive. It is late. You are probably compiling something in the background or, staring at a terminal window.
Yeah, or just unwinding after a really long day of tracing bugs.
Exactly. Pull up a chair. Tonight, we have a mission. We are unpacking a massive stack of sources. We've got the really detailed architectural teardowns from the LLM Mastery series.
Right, and the foundational papers, too. Like K-Ming Mashah, his original 2015 ResNet paper.
Yeah, and Ayafan Segedi's work on batch normalization. And we are zeroing in on what I genuinely think is the greatest historical debugging story in artificial intelligence.
It really is. The invisible wall.
Right, the wall that just stopped early deep neural networks dead in their tracks. Because it's the ultimate software engineering mystery, right?
Oh, absolutely. I mean, the community had this architecture that was theoretically sound. Everyone knew that adding layers gave the model more power to represent complex functions.
Because 8 layers gave us AlexNet.
Right, and 22 layers gave us GoogLeNet. So the logical next step for any engineer looking at those results is just scale it up.
Build 50 layers. Build 100.
Build 100, exactly. But when researchers actually tried to push from 20 layers to 50 layers, the network didn't just hit a plateau, the training error actually increased.
Which completely breaks standard engineering intuition.
It really does. The 50-layer network performed worse than the 20-layer network.
Because if you allocate more resources and, more parameters to a system, you expect it to perform better.
Yeah.
Or, at worst, it just memorizes the training data and overfits.
Right.
But a higher training error means it is fundamentally failing to learn at all.
And the sources make a critical distinction here between capacity and learnability. Mathematically, a 50-layer network absolutely has the capacity to represent any function a 20-layer network can.
Right. It could just copy the first 20 layers and set the remaining 30 to act as pass-throughs.
Exactly. The breakdown wasn't in the theoretical representation. The breakdown was in the optimization process itself.
The training mechanism just fundamentally failed.
It failed completely. Which points us directly to a concept you really need to understand to grasp any modern AI system. The vanishing gradient problem.
Yeah, and to understand why that training mechanism failed, we have to look at how these networks actually update their weights. Because we all know backpropagation relies on the chain rule of calculus to calculate gradients.
Right, working backwards.
Right, it starts at the output layer, calculates the error, and passes that error backward through the network, layer by layer, all the way to the input.
And the gradient at any given layer is a product of the gradients of the layers above it.
And the operative word there is product.
Yes. Multiplication.
Sequential multiplication is the fatal flaw in that early architecture.
Yeah.
Because when you chain multiplications together across dozens of layers, the mathematical stability of the entire system just degrades exponentially.
The LLM mastery notes actually use this incredibly vivid analogy for this sequential multiplication.
Oh, the 50-story building one. I love that one.
It's perfect. Imagine you are standing at the top of a 50-story building, and you need to send a really crucial set of instructions to someone on the ground floor.
But no phones, no elevator.
Right, no tech at all. You just whisper the message to the person on the 49th floor who whispers it to the 48th floor. Person, all the way down the stairs.
But every single time the message is handed off, the person rewriting it loses exactly 10% of the accuracy.
And breaking down those numbers exposes the sheer brutality of exponential decay. Because after one person, one floor down, you retain 90% of the original message.
Which seems fine.
It seems fine, right? But after 2 floors, you are at 81%. Drop 5 floors, and you are at 59%.
So by the time that message traverses all 50 floors,
which is 0.9 to the 50th power,
you are left with just 0.5% of the original signal.
Half of 1%. The message reaching the ground floor is literally indistinguishable from random noise.
And that maps perfectly to the learning signal, the gradient in those early deep networks.
Exactly, because the gradient signal starts strong at the output layer where the loss is calculated. But as it propagates backwards, it gets multiplied by the local derivative of each layer's activation function.
And if those local derivatives are consistently less than 1,
the gradient shrinks exponentially. By the time it reaches the early layers, it is vanishingly small. And if the gradient is effectively 0, the optimizer takes a step size of 0.
The weights just do not update.
They stay exactly the same.
And looking at the actual math detailed in these notes, the speed of that decay is terrifying. Because in the 1990s and early 2000s, the standard activation function everyone defaulted to was the sigmoid function.
Right, the S-curve.
Yeah, which squashes any input into a probability between 0 and 1.
And the architectural bottleneck there is the derivative of that sigmoid function. If you plot it out, the maximum possible value for the derivative of a sigmoid is 0.25. And that is only when the input is exactly 0.
Yeah.
For almost all other inputs, the derivative is much, much closer to 0.
So I'm looking at a table in the source material mapping out the best case scenarios here. If we assume every local derivative hits that absolute maximum of 0.25, the math still destroys the network.
It's unavoidable.
0.25 to the power of 10 layers shrinks the gradient to roughly 1 in a million.
Yeah.
By layer 20, 0.25 to the 20th power, the gradient is 1 in a trillion, 10 to the negative 12.
The early layers receive absolutely 0 usable signal. Their weights remain permanently stuck wherever they were randomly initialized at the start of the training run.
So only the final few layers, the ones closest to the loss function, are receiving enough signal to actually update their weights.
Exactly. And as an engineer building these systems, you might wonder, why does it actually matter if those specific early layers remain frozen?
Right, because the later layers are the ones generating the final classification or token prediction anyway.
But it matters deeply because of the feature hierarchy deep neural networks rely on. In a computer vision architecture, the very first layers are responsible for learning the foundational primitive features.
Like detecting raw edges.
Raw edges, basic color gradients, simple textures.
And in a language model, the early layers handle the initial token embeddings and rudimentary syntactic relationships.
Right. So if those early layers are outputting garbage because they never trained, the later layers are trying to build complex abstractions out of pure noise.
It's like trying to recognize a face or understand a complex sentence from a TV staticky screen.
Exactly. You are feeding the functioning part of your network corrupted data from the start. It's like building a skyscraper where the first few floors are a random, unstable mess.
No matter how nice the penthouse is, the building fails.
Yeah.
Adding layers just diluted the forward pass with layers of untrained, random matrices.
It was self-sabotage built into the math.
But my mind immediately jumps to the inverse problem. We just walked through what happens when the multiplication factor is strictly less than 1. What happens when the local gradients are consistently greater than 1?
Oh, then you trigger the vanishing gradient's evil twin.
Exploding gradients.
Yes, exploding gradients. Instead of the signal decaying exponentially into nothing, the signal compounds exponentially into chaos.
And the notes model this out too. If the multiplication factor is just 2, chaining that across 50 layers gives us 2 to the 50th power.
Which is massive.
That is over a quadrillion, 10 to the 15th.
Yeah.
Anyone who has monitored a training loop knows exactly what happens to the loss curve when gradients hit a quadrillion.
The parameters update with steps so massive they overshoot the optimal minimum completely.
Right.
The loss function stops decreasing, starts oscillating wildly across the optimization landscape, and inevitably overflows. You hit NaN.
Not a number.
Not a number. Your training run just crashes. It is the mathematical equivalent of audio feedback, where the microphone picks up the speaker, amplifies it, and instantly creates a deafening screech that blows the system.
Hitting NaN during a massive distributed training run is a total nightmare. The immediate fix I always see in code bases is gradient clipping.
Yes.
You either use value clipping, where you hard cap individual gradient values between, say, -1 and 1, or you use norm clipping, where you scale the entire gradient vector down if its total magnitude exceeds a certain threshold.
And norm clipping is generally preferred because it preserves the directional vector of the gradient. It just reduces the step size. It acts as a safety valve.
Like a speed limiter on an engine.
Exactly. The engine wants to go 300 kilometers an hour, but the limiter caps it at 120. If the network tries to take an update step that would throw the parameters into infinity, the clipping mechanism steps in and truncates the vector.
It prevents the crash.
Yeah.
But reading through these architectural teardowns, the authors are very clear that clipping is merely bounding the symptom.
It's just a Band-Aid.
Right. It doesn't fix the underlying exponentially curved math of the architecture.
Clipping keeps your training loop alive, but it forces your optimizer to take extremely inefficient, constrained steps through a highly volatile landscape. To actually scale deep learning, the community had to fundamentally re-engineer the architecture, so the math naturally preserved the signal.
And that took a decade of compounding breakthroughs, starting with replacing that sigmoid activation function.
The switch to the rectified linear unit, or ReLU.
ReLU. The elegance of ReLU is just its computational simplicity. The function is simply the maximum of 0 and x. So if the input is positive, the output is exactly the input,
Right. And the derivative of x for any positive number is exactly 1.
which is the magic number here.
It is the magic number. By using ReLU, when backpropagation chains those local derivatives together, it is repeatedly multiplying by 1.
The gradient doesn't shrink to a trillionth of its size.
And it doesn't explode into a quadrillion. It passes straight through the positive activations entirely unimpeded.
That solves the positive side perfectly. But wait, if the function is the max of 0 and x, any negative input outputs a hard 0. Does the derivative just flatline for the entire negative half of the distribution?
It drops to exactly 0. If a neuron's preactivation value falls below 0, it passes no gradient backward whatsoever.
None.
None at all. And this introduced a new hardware-level bug known as dying ReLUs.
Dying ReLUs.
Yeah. During training, a large weight update could push a neuron's weights into a state where it always outputs a negative number for any input in the dataset.
Oh, I see.
And once that happens, the gradient is permanently 0. The neuron can never update its weights to recover. It is effectively dead space in the network.
Which totally explains the evolution we see in modern networks. The teardowns show the transition to leaky ReLU, which allows a tiny non-zero gradient for negative inputs,
Right.
and eventually to GLU, the Gaussian error linear unit, which modern transformers use to provide a smooth, mathematically continuous curve instead of that hard 0 cutoff.
Exactly, but fixing the activation function was really only the first piece of the puzzle. The notes heavily emphasize that even with ReLU, deep networks wouldn't converge without a revolution in weight initialization.
Right, you can't just start with random uncalibrated weights. You need a Goldilocks zone.
Early on, engineers were initializing network weights using standard normal distributions. But if you initialize a matrix of weights randomly without accounting for the geometry of your network, the variance of your activations shifts dramatically as data moves forward.
How so?
Well, think of it like a chain of audio amplifiers. If you have 500 inputs feeding into a single neuron, a really large fan-in, the dot product sum has a naturally much larger variance than a neuron with only 10 inputs.
So the signal gets wildly stretched or compressed just by passing through the raw, untrained weights. If each amplifier doubles or halves the volume, you get either deafening noise or pure silence at the end.
Exactly. So Xavier Gloro and Yoshua Bengio proved mathematically that to maintain a stable learning environment, the variance of the activations must remain identical across every single layer.
So Xavier initialization.
Yes. Their solution, Xavier initialization, scales the initial random widths by dividing them by the square root of the number of input neurons. It perfectly calibrates the volume so the signal doesn't artificially grow or shrink simply due to the layer's width.
And then Kaming, he took that a step further for ReLU specifically, didn't he? Because Xavier initialization assumes the activation function is symmetric around 0.
Right.
But ReLU chops the entire negative half off. It basically cuts the variance in half. So He initialization multiplies the variance by 2 to compensate for the dead half of the ReLU distribution.
Yes. That combination of ReLU and He initialization allowed networks to push deeper than ever before. You preserved the gradient derivative at 1, and you preserved the variance of the forward and backward passes.
But they still hit a wall.
They did. As networks grew, engineers encountered another critical instability. The internal environment of the network during training was still too chaotic.
And that brings us to the 2015 breakthrough from Ioff and Segedi, batch normalization. The paper outlines a problem they called internal covariate shift.
Internal covariate shift happens because layers update simultaneously. As the weights in Layer 1 update, the statistical distribution of Layer 1's outputs changes.
But Layer 1's outputs are Layer 2's inputs.
Exactly. This means Layer 2 is constantly trying to map its weights to a moving target. By the time you reach Layer 20, the input distribution is shifting so violently with every batch that the optimizer cannot find a stable path to convergence.
The math behind the batch norm fix is surprisingly direct, though.
It really is.
For every single mini batch of data passing through a layer, the algorithm calculates the mean and the variance of those specific activations. It then normalizes them, forcing the activations to have a 0 mean and unit variance.
It centers the data perfectly. It's like climate control for a building. Instead of every floor having wildly fluctuating temperatures, batch norm keeps every floor at a comfortable 22 degrees so learning can actually happen.
I like that.
But Ioff and Segedy realized that strictly forcing zero mean and unit variance could severely restrict the representational power of the layer. Maybe the optimal distribution for a specific feature shouldn't be centered at zero.
Right.
So they introduced two learnable parameters per channel, gamma and beta. Gamma scales the normalized activation, and beta shifts it.
So the network normalizes the chaotic variance to stabilize the training step, but then retains the mathematical freedom to scale and shift that distribution wherever it actually needs to be for optimal accuracy.
Exactly. It smooths the optimization landscape so drastically that engineers could suddenly increase learning rates without crashing the model.
Batch normalization was totally transformative. But even with ReLU, initialization and batch norm, the community hit another wall.
They could reliably train up to about 30 layers.
But when they tried pushing to 50 or 100 layers, the accuracy degraded again.
The optimization landscape of 100 sequential transformations was simply too highly non-convex. The gradients weren't vanishing mathematically anymore, but the sheer complexity of the path made learning nearly impossible.
Which sets the stage for what the LLM mastery notes call one of the top 5 ideas in the entire history of deep learning. Caning. His 2015 paper introducing residual networks, ResNets.
The ResNet architecture introduced the skip connection, and it fundamentally altered how we design neural networks.
Okay, break that down for us.
In a standard feed-forward network, a layer takes an input vector, x, and applies a nonlinear transformation to it. The output is purely f of x. The layer is forced to learn an entirely new mapping from scratch.
But Caning, he changed the core equation.
He did. In a residual block, the output equals f of x plus x.
Plus x. That is the skip connection.
Yes. You take the original input tensor, route it completely around the transformation layers, and perform an element-wise addition with the output of those layers.
The notes use a brilliant highway analogy to visualize why this is so powerful. Imagine you are driving a route with dozens of checkpoints.
Okay.
In a standard sequential network, there's only one road. A winding, highly complex mountain pass representing the transformation layers. Every single time you navigate a tight corner, you lose momentum. Over 100 mountain passes, the gradient signal loses all its velocity trying to navigate the complex topography.
The skip connection builds a straight, multi-lane highway directly alongside that complex mountain road.
Exactly. You still have the mountain road if the network needs to apply a complex, nonlinear transformation to the data.
Yeah.
But you also have this straight bypass.
Yeah.
Because the derivative of x, the identity function, is exactly 1.
The gradient can flow backward down that highway at full velocity.
Skipping the complex transformations entirely, delivering an undiluted learning signal directly to the earliest layers of the network.
Furthermore, the transformation layer, f of x, no longer has to learn the entire mapping. It only has to learn the residual, the minor adjustment or difference needed on top of the original input.
And the empirical results of this architectural shift were staggering. With residual connections, his team bypassed the 30-layer limit entirely. They didn't just train a 50-layer network.
No, they trained a 152-layer network.
That is a 7.5x leap in architectural depth, executed practically overnight.
And it shattered every existing benchmark on the ImageNet dataset, surpassing human-level performance for the first time. The skip connection works because it makes learning identity mapping trivial.
Learning to basically do nothing.
Right. If a network determines that a specific layer isn't actually needed for a given task, it simply pushes the weights of f of x towards 0. The skip connection handles the rest, passing the raw data straight through. Deep networks could suddenly feature hundreds of layers without forcing the optimizer through a labyrinth of sequential transformations.
Bringing this massive history lesson into the present day, these teardowns make it explicitly clear that everything we just analyzed forms the absolute bedrock of the modern AI stack. Because anyone making API calls to GPT-4 or Claude or deploying a local Llama model is relying on these exact engineering patches.
If you open up the transformer architecture, the engine powering every modern large language model, you see the direct lineage of these solutions everywhere. You see GELU activations maintaining gradient flow.
Right.
You see layer normalization and adaptation of batch normalization designed specifically for sequential token data stabilizing the internal variance. You see mathematically rigorous, depth-scaled weight initialization.
And transformers are fundamentally built entirely around residual connections.
Entirely.
The core equation for every single attention and feed-forward sublayer in a transformer block is layer norm applied to x plus sublayer of x. Without that plus x, without the gradient highway routing around the attention heads, training a model with 100-plus layers would be mathematically impossible.
The error signal would decay into noise before it reached the initial token embeddings. It reveals a profound shift in how we approach AI architecture. For decades, the focus was entirely on representational capability. We asked, does this matrix have enough parameters to model human language? But the historical bottleneck wasn't capability.
It was learnability.
It was learnability. Information has to flow flawlessly in two directions, forward for inference and backward for backpropagation.
Building an architecture that can theoretically represent the world is totally insufficient if the learning signal cannot physically traverse its own depth to update the parameters.
Engineering that stable two-way gradient highway is what actually unlocked the era of large-scale deep learning.
We went from an invisible wall, where sequential multiplication annihilated our gradients into trillionths of their size, leaving the earliest foundational layers to output random noise, to engineering skip connections that let us effortlessly stack hundreds of layers. Studying how these fundamental bugs were diagnosed and mathematically patched gives you a much sharper lens for analyzing the massive billion-parameter code bases we work with today.
It really does. And, we discussed how residual connections allow a neural network to trivially learn an identity mapping, effectively letting unnecessary layers opt out by pushing their transformations to zero and passing the data straight down the highway.
Yeah.
This raises a really interesting possibility for the future. If these massive architectures already possess the internal mechanism to bypass layers during backpropagation, could we engineer dynamic AI models that intentionally power down entire blocks of layers during inference?
Oh, that is fascinating.
Imagine an LLM that physically shrinks its active processing depth in real time when answering a simple query, and expands to utilize its full depth only for complex reasoning. It would save staggering amounts of parallel compute.
I will leave you with that to think about. That is our time for tonight. We hope this deep dive into the vanishing gradient gives you a new appreciation for the optimization math running quietly inside your models. Keep exploring the deeper mechanisms of your code. Have a great night.